Hello again. This is a CS3344 video 3. We had just finished one example of a context-free grammar, context-free language. Let's do another, example 2. S, regular old start symbol. S can be replaced by A, S, B, where A and B are lowercase, S is uppercase. That means something, according to convention. Or wait, it can also be replaced by just lowercase a, lowercase b. Seems fairly simple. Let's see if we can answer a simple question about it. What's, short for what is, language generated by S, or language defined by S? Oh, I don't know. It's so complicated. Let's try it. Just a couple of derivations. S can go to AB. Well, whatever the language is, AB is in it. An alternative, a different derivation, S goes to a SB. I'm going to underline capital S because I'm going to replace that next. I'm going to replace it with ASB again. Not a whole lot of choices. ASB, and it's still got the B at the end that was already there. Rapidly, we see a pattern developing, so I think I'll close this off. And this time, replace S with just AB. A, B, B, B. So the answer to the question, LS equals, you know what? It's A to the N, B to the N, where N is greater than or equal to 1. Let's pause and reflect on that for just a second. That's like the classic non-regular language. So already, with a simple context-free grammar, already we can do things that we were not able to do with regular grammars, regular languages. Why not? What was the secret? There were so many secrets hidden in that pumping limo, weren't there? Some of them were just too secret for us to fully understand. All the business about the secret number of states and everything. Here's another secret. What can a regular language not do that apparently a context-free grammar can do? Can count. Regular languages were not capable of matching the number of A's to the number of B's. Couldn't do that. I think of it as run and gun. It was a one-way trip. The regular grammars, when you look at those, they build strings from left to right with no looking back. Look what this one's doing. This is pushing stuff out from the middle. It can push out a B to match every A that it pushes out to the left. So since it's springing up from the middle, pushing things out to the side, then it has no problems generating A to the N, B to the N, where N greater than or equal to 1. It almost seems unfair. That was just too easy. What about this example? I'll put it up here next to it. Assuming were there any questions about this example? I'm sorry. Old habits die hard. If there are, write them in the margin and bring them up in our face-to-face chat session or office hours. What's this one? S goes to, you know what? A, S, B, or epsilon. Well, at some point, it just gets so simple that I'm not going to elevate it to writing an answer on the board. Is this the time? What's the difference here? Oh, okay. I'll write it on the board. Oh, I wrote this wrong, and you let me get away with that? It's not the language of S. It could be that, the language that's generated by grammar S. But I need to specify the entire grammar, not the start symbol. Good heavens! Erase your copy of the YouTube video and replace that so it's not embarrassing for me. Okay, over here, what's the language of this grammar? Not the language of the starting symbol. Okay, the language of the grammar equals, same thing, A to the N, B to the N. Except, man, I believed at this point, didn't I? Except N doesn't have to be greater than or equal to 1. N is greater than or equal to 0. Because epsilon is also in the language, the start symbol can be replaced with the empty string. Okay? The more examples we look at, this is my justification for continuing here. The more examples we look at, ideally, the better this is going to sink in. Example 4. I made that grandiose statement that context-free languages, context-free grammars have so much more applications in computer science, or at least a bunch more than the others do. So let's put my money where my mouth is. Let's do arithmetic expressions, abbreviated. Arithmetic expressions. That's what that's supposed to mean. My grammar is going to have start symbol E for expression. E can be replaced by E plus E, where I'm going to get stingy with word space already and describe this rather than write out and elaborate and comment all this stuff. The capital E, of course, that's a non-terminal. The plus sign itself here is a terminal symbol. It shows up in the sentential form. It's a valid thing to show up in the right-hand side of one of my derivations, but I don't replace the plus with anything. Maybe I don't want to add them. Maybe I want to multiply them. So instead of E plus E, expression plus expression, I might want to substitute E times E. That would also generate a valid expression for me. I might, just might, want to put parentheses around it. Parentheses E, and now I'm starting to regret not annotating all this stuff. Here are the terminal symbols I've introduced so far. The plus sign, the times sign, the open parenthesis, the closed parenthesis. All of those are in capital sigma. All of those are terminal symbols in this language. Or, so is lowercase a. Now, this is kind of an abstract class. You're used to that. But this is very abstract, and it doesn't look like arithmetic expressions at all. But E is a stand-in for any valid arithmetic expression. The plus sign is actually a stand-in for itself. It is a plus sign, but also a minus sign. That could be a minus sign, and it's just going to complicate what our strings look like, plus or minus either one. Adding is the same as adding a negative. Times sign, actually, that's actually a stand-in for times and divide. I'm kind of regretting going this direction prematurely, but I've already done it, so there's no backing out now. The parentheses are in case I want to enclose an expression in parentheses. This is a sentential form, but it's not a string of the language because I still got to replace the E. The A all by itself, good grief, that's a stand-in for a bunch of stuff. That's a stand-in for a number, a variable, anything that is part of a valid part of an expression that I might want to represent for a computer language program, or even just a regular mathematical expression, arithmetic expression to solve. A is pretty powerful. That's a number, a variable, all that kind of stuff. So there we have it. E can be replaced with any of those 4 things. And just to try it out and see what's going on here, here's our leftmost derivation. Come on, caffeine, do your stuff. Leftmost derivation. I'll start with E. That's the start symbol. I'm going to replace E with, I'm in the mood for addition. E plus E. And it goes without saying in a leftmost derivation that that's the thing I got to replace next. But I'm going to keep things as clear as possible and underline that to show, yeah, I know. I'm still going to show you what I'm replacing. I'm going to replace that E with this, E times E. E times E. And there I have replaced this first E that looks like a poorly written E. I've underlined it. I'll make the underline nice and bold. There. I replaced that with E times E, and the plus E is still hanging out there. So far, so good. Now, here's a convention that I really like, because I like reducing my workload, even though it's very difficult to do these days. If I'm going to use identically the same production multiple times going from one step to the next, that I could put a little number over here. Because what I'm about to do is replace each one of these E's with a single A. And since that is one production, capital E can be replaced by A, and I'm using exactly that same production 3 times in a row, it's still not violating the rules of leftmost derivation. It assumes that I'm replacing this one first, the next line I replace that one, next line I replace that one, I'm combining them all into one big replacement, and I end up with the final expression, A times A plus A. Not terribly complicated, but that's just, remember, that's the stand-in for a variable or a number. Some number times a number plus a number. They don't even have to be the same number. I mean, in the full-blown grammar, while I'm trying to represent all possible mathematical expressions, I would not have lowercase a here. I would actually have another non-terminal that could be replaced with 0, 1, 2, 3, 4, 5, any number. I mean, it probably is replaced with some other non-terminal symbol called number and so forth. But that's a stand-in for a specific number. I am getting lost in the details on this. I'm sorry about that. Or, this is another leftmost derivation, still leftmost, still derivation. I could not necessarily start off in a mood for addition. Let's not. Let's do e times e. Yeah, that just feels wild, crazy different, doesn't it? Then, leftmost derivation rule. I'm going to replace e with a big bold underline. I'm going to replace that with an a already. A times e. Now I've only got one non-terminal to replace in the next step. And I'll replace that with e plus e, just to mix things up. So I'll have still the a times up front, and this e will be replaced with e plus e. And this is getting old fast, so just like we did before, I'm going to combine steps here and say I'm going to replace both of those e's. A standard way would be just to indicate that I'm using exactly the same production rule twice here. A times a plus a. And I'll step back and take a sip of tea while you admire our handiwork so far. And you have an observation to make, don't you? Your observation is exactly right. This grammar is ambiguous. Oh, exclamation point. Because that's typically considered to be a bad thing. What does it mean? What does it mean that this grammar is ambiguous? There's more than one way Well, no, I'm not going to say one way. That is way too generic. There's more than one leftmost derivation that generates the same string. I'm yelling everything, exclamation points everywhere. Before you know it, I'll be writing in all capital letters. This grammar is ambiguous. I know that's a new word. I just looked it up on you. But here's what it means. I can end up with the same string of the language, but using different leftmost derivations. These are not the same. I replace different symbols at different times. That's generally considered a bad thing. Why? Well, where we're going to with this a little bit is we're going to be actually looking at context-free grammars that generate either simple computer languages or, you know what, maybe the whole real thing. Maybe we'll just look at a grammar that generates a C language. If there's more than one way to generate a mathematical expression, an arithmetic expression, that means there's more than one way to evaluate it. What part of what a compiler has to do is parse what you've typed in. You didn't type this in. You typed in 3 times 5 plus 9. If you do that, and there's no parentheses anywhere, the compiler's got to figure out, which one am I going to do first, the times sign or the plus sign? Each one of these actually corresponds to evaluating one of those operations first. As we go backwards from this, in other words, as we parse this expression back to a single symbol, look at this. The first thing to collapse over here is the multiply, which would indicate to the compiler, I better multiply these before I add to get the value of that expression. This one over here, we would view this as incorrect. It violates the order of operations. The first operator to disappear over here is the plus sign. as we're going backwards, trying to figure out what might this expression mean? What order do I have to do these operations to get the correct value for this expression? This one would collapse the plus sign first, do the addition first, and then the multiplication. So that one's actually wrong. That grammar would not be good for evaluating arithmetic expressions. Oh, if only there were some solution to this. Oh, well, just like a soap opera, you're going to have to wait till next time. See you online.